In this video, we're going to talk about how to run an ANOVA in SPSS and interpret the output. And we're also going to talk about factorial ANOVA, which is an extension of ANOVA, as well as how to conduct something called post hoc tests after you've run your initial ANOVA. So, analyze invariance. So let's say we wanted to calculate an ANOVA statistic using SPSS. Well, the process is actually relatively simple. You would go to the Analyze option, and I'll show you this in a separate video as we work through the classwork. But here's some helpful screenshots. So we go to Analyze, Compare Means, and then down here to One-Way ANOVA. So this is the same option we used when we conducted our t-test, and also we want to create descriptive statistics broken down by group. So we click on One-Way ANOVA, and it's going to bring up a dialog box like this, and it has a dependent variable list, and you can't see it because the red's on top of it, but it says factor. So this is basically our independent variable and our dependent variable. So in the example here, it has the bowling data where we're looking to see if there's a difference between bowlers. So the bowler is the independent variable, and that's supposed to predict the score, which is the dependent variable. And in ANOVA, the factor always has to be a categorical or nominal level variable. The dependent always has to be a scale level variable. If you change that, you change the technique you use. When you run the test, you'll get a table that looks like this, an ANOVA table. And you're going to have the sum of squares between group sum of squares, within group sum of squares, total sum of squares, the degrees of freedom, something called the mean squares, and then the F statistic and the significance level. So this is giving you the same information that you got when you worked this out by hand for the practice problem. So computer did it for you though. So you get the between, within, total, divide by the degrees of freedom, that gives you the mean squares. You divide 31 by 5, and you get your 5 right here. The computer does you the favor of looking up the associated p-value, in this case 0.019, which is under 0.05, so we conclude that yes, there's a significant difference between the groups. Life after ANOVA. So you calculated the ANOVA test statistic, and you've determined whether or not there are any statistically significant differences between the groups. Well, chances are you still want to know more, specifically which groups are different. So as you recall, ANOVA is an omnibus test. It just lets you know if there's any difference anywhere. If it's non-significant, so let's say this was 0.08 or even 0.051, 0.99, it's non-significant, we can conclude that there are no differences anywhere. But once it's significant, like it is right now, there could be, in this case we're comparing 3 groups, there could be 1, 2, or 3 significant differences. We don't know how many, and we don't know which ones. That's why ANOVA tests are usually followed up with other tests designed to determine exactly which means differ. Now, that's technically not the right way to go about this. There's something called planned comparisons, and basically the way that works is you can only split the variation and the variance in particular ways, and so you decide I want to compare these groups to this group, and then within those you'd break it up. It's sort of hard to explain and sort of complicated to do. So we're not going to do planned comparisons, but I want you to know they exist. So if you were to do your own study and use ANOVA out in the real world, you would actually take that into consideration. You probably would run planned comparisons. What we're going to use are called post hoc comparisons, and that simply means after the fact. So in this case, we've run the ANOVA, and now we're sort of exploring. So this is considered exploratory analysis, and we want to see, well, where were the differences, right? So this isn't technically the right way to go about it, but it is important to know how to do this, and you'll see a lot of studies reporting post hoc comparisons. Sometimes the studies will present that as though that's sort of the proper way to find them. Other times the study would say, well, here's our planned comparisons, and then we went back later and did this, so you'd have to replicate this, blah, 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 blah. But just so you know, here's what the comparisons were. So in our bowling example, there were 3 players, Lori, Robert, and John. In a t-test, you can only make one comparison. The ANOVA lets you compare all of them. We've seen a significant statistic, so we know that there's at least one difference, but we don't know which of these comparisons is significant or multiple, right? So there's 3 possible post hoc comparisons: Lori versus John, Lori versus Robert, John versus Robert. It's all the combinations. So to run a post hoc comparison, you'd run your one-way ANOVA just like you always would. It's the same dialog window. So factor is bowler, dependent is score. bowling score. And you click on this button here that says post hoc. When you click on that, you get a window that looks like this. It's a post hoc comparison dialog box, and you have all these different choices. So all of these are different kinds of post hoc tests. And the two that we're going to monkey around with are the first one, LSD, and then the second one, Bonferroni. LSD stands for least significant difference, and Bonferroni stands for Mr. Bonferroni, who came up with this test. So what we do, again, I'll show you this in the classwork video. I'll walk through this in real time. But what we'll do is we'll pick both of these, and the significance level we're going to leave at the default level, which is 0.05. So what these do is they're types of corrections, and essentially we're trying to correct for type 1 error by raising the bar. So instead of just running multiple t-tests, this right here, this Bonferroni correction, what this does is it sort of takes the total amount of significance we're comfortable with, 0.05, and then divides it by the 3 comparisons. So our type 1 error rate stays the same, even though we get to do multiple comparisons. This top one, LSD, least significant difference, it's sort of like doing 3 t-tests. So it dredges the bottom and lets you know, is there any possible way this would have been significant, but you'd be very cautious about interpreting those findings. So now, when you run the ANOVA, if you've chosen these tests, you get a second table called multiple comparisons. Right? And this is it. Again, significant at the 0.05 level. You can change that if you want to. So the first group here, this is the LSD, the least significant difference test. The second one is the Bonferroni. So this is giving you the same information, but with different corrections. This one's more liberal, this one's more conservative. Also within these, actually you get all the information twice. So these are different comparisons, Robert versus Lori, Robert versus John. Well, down here is Lori versus Robert. So this is the exact same thing flipped around, right? So the exact same values, 0.694, 0.694. So everything's repeated. So it shows you 6 comparisons when in fact there are only really 3 different ones. Anyway, let's take a look. So Robert versus Lori. Well, there's a difference of 0.6. So Robert scored 0.6 less than Lori in terms of his mean. The standard error is 1.48, the significance 0.69, and look at the confidence interval around that difference. It includes 0. So there's no significant difference between Robert and Lori's score. What about Robert and John? Well, Robert's here, John's here. The mean difference is 4. That means that Robert's mean was 4 higher than John's. The significance level is 0.02. And the confidence interval does not include 0. So he performed at least 0.75 better than John, and his high is 7 better than John. So there was a significant difference between Robert and John's scores. Well, this leaves out Lori and Robert. I'm sorry, that's not right. This leaves out John and Lori. So we go to right here, either Lori John or John Lori, same thing. And there's a difference of 4.6, so Lori performed 4.6 over John. Significance level 0.009 does not include 0. So again, there's a significant difference between Lori and John's scores. So basically, Robert performed above John, Lori performed above John, but Robert and Lori were tied. So even though the means are different, it's a statistical tie. Down here is the Bonferroni correction. So what happens down here is it gives you a more conservative estimate. It takes that 0.05 and chops it up between the 3 comparisons. So to illustrate this point, let's look at John and Robert. So down here on the LSD, it said it was significant, right? 0.02. But now let's look at John and Robert. It's still a difference of 4. But the significance level is 0.06, non-significant, and the confidence interval includes 0. So using this more conservative correction approach, this difference becomes non-significant. So it matters which option you choose, and it's going to affect your interpretation. All right. So here it is, sort of blown up. So comparing Robert and Lori, the mean difference is 0.6, non-significant. Robert and John, difference of 4. It is significant, right, under the LSD criteria. But under the Bonferroni criteria, notice that it is no longer significant. So this is the more conservative criteria. Okay, so how do you report this? So you have to report your results in APA format. So it's an F statistic. So we have a capital F in italics, and then in parentheses, the degrees of freedom. So between group degrees of freedom, comma, space, within group degrees of freedom, parentheses, space equals space, the statistic rounded to the hundreds place, 5.65, comma, space, P in italics, space, less than, space, 0.05 in this case. And there we go. What about the hypotheses? Okay. Well, the null hypothesis is that all the means of the population are equal. So the mean of Robert equals the mean of Lori equals the mean of John. This means that if you were to consider every possible frame that could be bowled by each of these players out in the real world, out in the population, they would all be equal. That basically all three are equally good players. So if there's a difference, if Lori's score is higher than John's, it was just by coincidence that it happened this time, but if we did it again, it could go the other way, right? That's what the null hypothesis is. The alternate hypothesis is that there's differences between these. The alternate hypothesis for an ANOVA is written a couple different ways. The textbook we used to use wrote it this way, and this really actually isn't right. You'll see this, but it's actually not correct. The alternate hypothesis is that there is a difference between the means. So see, this suggests that all of them have to be different, which is not the case. If anything's different, that violates the null hypothesis. So it should be that there is some difference between the means of the three groups. And again, X bar, so these are sample means.